Hi, so this is part two of problem 1.17 for exam two, part two. We just went for Dr. Ko's transport two class. We just went over how we are going to make our initial guesses. So, we just went over, what our initial guesses were going to be. We just solved for those, the order of magnitude of them. And now we're actually going to apply these initial guesses to a system of equations in an initial value problem, and we're going to hopefully find the solution to what the mole flux of acetone and methanol are when eta is 1, and we have ways to check that. And we are also going to plot eta versus the mole fraction of all three components, air, methanol, and acetone in this system. And we are going to plot all three of those against it and see how they compare. And yeah, so let's get going. First of all, we're going to import NumPy, which is numerical Python, as NP. That is just something we need because numerical Python has all these root solvers like optimization tools, integration tools, and we're actually going to go right into those. We're going to go from SciPy dot integrate, which is an integration toolbox. We are going to import the solve IVP function, which is this will help us solve our initial value problem once we create it with our Stefan-Maxwell diffusivity equations. And we're also going to take from SciPy dot optimize. What can I type? We are going to import IVP again. We're going to import root as a root solver because if our guesses are not correct, our goal is that our guesses have the correct order of magnitude, so they're close enough that we will find our molar flux values of acetone and of methanol at the eta is 1, the top of the Stefan tube. But however, if they're not correct, which most likely they won't be, we want a root solver to find these roots for us. So we're also going to import some graphing tools so that way we can make this eta versus mole fraction plot at the end. So I'm going to go from plotly.subplots. I'm going to import a thing that'll help us make our subplots. Make subplots, not subplots. There it is, subplots. All right. So before we go on, we need to add one more thing. We need to import plotly dot graph objectives. I believe it is plotly dot graph objects. And we're just going to define that as something small, like with NumPy we did NP. We're just going to do geo graph objects because we're going to need that later. When we have three different functions on the same graph, we're going to need this tool to be able to plot each of our functions. So knowing that, we are going to go down here to our given information. This is actually the information given in the problem. All this is given. The only thing I did is I converted units from millimeters squared per second to meters squared per second for all these Stefan-Maxwell diffusion coefficients. And I also changed the pressure from kilopascals to pascals because these will all conform now in our equations once we put those in. And the other thing I did is I added our initial guesses for the molar flux of acetone and methanol that we defined in part 1. So knowing all of this, let's get on with our coding. First, we're going to have to create some relationships. So knowing that this is a boundary, excuse me, I'm gonna work on this for a while, but knowing this is a boundary layer value problem, we know that we need to use a thing called F12, which we will define in a second. But in order to have F12, we need concentration. We know that concentration is pressure divided by the constant R times temperature. And knowing that concentration is that helps us a ton here because we have pressure, temperature, and we know the constant R is, so we can find concentration through that. Well, oh, I don't want to do that. Sorry. Concentration, the reason that it is relevant here is when we're doing a boundary layer value problem, we have F12, and what F12 equals is concentration multiplied by your Stefan Maxwell diffusivity coefficient divided by delta. So we needed to define our concentration up here so that we can have it in all three of these. I keep doing that. In all three of these F1, F2, F3 when we define those, because that's what it's defined as in the book. So again, we'll just do concentration of D13 divided by delta, and then we will do the final one. F23 equals concentration times the Stefan Maxwell diffusivity constant between 2 and between 2 and 3 divided by delta. And we're just going to define those quickly because we'll need those when we're using our equations. And this is a boundary layer value problem, which uses F1, 2, F23, and F13 instead of D12, D1 or D23 and D13 as we saw earlier in the other problems. So knowing all that too, we are also going to go into we're gonna have to go into what this solve IVP function actually means, because say we just try to use like solve IVP of where is it up there underscore IVP. Like, what does that actually mean? Like, we're solving an issue value problem, but we don't know what we need to define, what we need to find in order to have it solve it for us. Well, the great thing about Python is it helps you out. So I took and solve IVP and I see, okay, I need to find a function, a time span, a dependent variable. I need to define the method I want to use and the dense output that I want to use. So I'm like, all right, well, knowing all of those things, I know I need to define a function. So first thing I'm gonna do is define a function. Let's just call it dy for our time span, which our time span here is eta because it's from 0 to 1. We know that's our position span, which will act as our time span here because it's our independent variable. And then our dependent variable here would be the molar fraction y. So knowing that, we are going to, what am I doing? I didn't define, sorry, I keep pressing shift enter. I'm going to define our dependent variables y. So y1 is equal to y of 0 because our indexes start at 0 in Python. Oh my gosh, I keep pressing shift enter. And if our indexes start at 0, then our first term would be acetone, which would be y1, the mole fraction of acetone. So now we have y2, which equals the second term in our index C here, which would just be y1. And then what does our great mole fraction of air equals? It just equals 1, which is what the mole fraction equals, subtracted by all the mole fractions of all the other components here, which is just y1 and y2. Beautiful. This we can now put in our equation. So we're going to put we want this to return us an array, which we have to do NP because that's numpy, it's a numpy array of all of our equations here. So I'm going to go to the book over here in a different tab. Hold over, and what do I got? Am I sharing this now? Okay, so I have y1 and 2 minus y2 and 1. So we're going to start with that. Which means, oh, and 1. Sorry. This means the mole fraction of acetone multiplied by the molar flux of methanol subtracted by the molar fraction of methanol multiplied by the molar flux of acetone. And this is all going to be divided by F12. And then we are going to go back, but I'm pretty sure it's subtracted by, yeah, subtracted by, because this is 0, as we defined earlier. Since N3 would be 0, since there's no more flux of air, we are just going to do subtracted by 1 minus 1, or y1 minus y2 times the molar flux of acetone divided by F13. So let's go back over here and do that. So we have F, wait, why did I do F? We have, what is this? It's not F, it's, oh, 1 minus y1 minus y2, yeah, that's what it is. 1 minus y1 minus y2, and then multiplied by n1 divided by f. Okay, there we go. We're going to do comma. We're going to do the second components here, which is just the same thing, but with component 2 and 3. So I'm just going to look at this. I'm going to go, and I'm actually just going to copy and paste this right here. So I can do less work. Less work is always better. Y1, so all these ones will become 2s, 2s will become 1s, 2s. Okay. 2, 1, 1, 2, and 1, 2 is going to stay. And then we have 1, 1, 2. This will be a 2, and this will be a 2. Oh, no, not the F. All right. So those are just defining our equations and typing them in. Nothing very big there. And we're going to see if that works. Oh, I forgot some. Nope, not semicolons, semicolons. Let's see if this works. Okay. So we know that works, and we know we typed those in right then. And then we're going to now say, let's say the result of our initial value problem is equal to the, what do we want to set this equal to? That's the best question. To the solve IVP probably, because we want it to be the result of this IVP, which will then give us what? We have to do all these things again, right? So we have to look, we have, okay, what? We have a function of dy. We have a time span of 0, 1 for our eta, right? That's our time span. So we have our function, our time span, we have our dependent variables, which we're actually going to put the initial value over our dependent variables. So it would be y1i and y2i, because that's what the initial value of our mole fractions are defined as up here. And then we are going to select our method, which my professor prefers Radu, and he's better at this than I am. So I'm going to go ahead and go with what he says. Radu. And then I'm going to also do the dense output, underscore output, and set that it's equal to false up there. We're actually going to set it equal to true, because what we want is we want the sorry, I'm getting confused. We want the initial value problem to be solved for all values of eta, because if it's solved for all values of eta, which true would do, then we can take this this array that has all of the initial value problems, or all, oh my gosh, sorry, all of the values of eta solved through this initial value problem. So that way we have, okay, here, let me re-explain this. I'm just gonna start, I'm confusing myself. The reason that we want this to be true is because we want this initial value problem to be solved for all numbers and values of eta. So that way, later in this problem, we can actually graph where or what the mole fraction is for each of these components at each value of eta, which is beautiful. But right now, we only want to determine the solution for this, or for one value of eta. And what is that value of eta? It's 1. It's 1 because we know that at the top of this Stefan tube, the mole fraction of acetone, the mole fraction of methanol will eventually be 0 because there's going to be so much excess air that we won't even have any methanol or acetone. Well, knowing that, we can check what this outputs to us, okay? So we're going to check what this outputs. And if this doesn't give us what we want it to, then we're going to, if this doesn't give us what we want it to, then we're going to, which would be what? Sorry, I'm confused myself. Okay, so we have here the, we know that the mole fraction must be 0 and it must be 1 when, not 1, must be 0 when eta is 1, okay? We know this because there's so much air at the top of this tube that we have so little of the acetone and methanol. Eventually it's just going to converge to 0, which if it converges to 0, that means that at 1, the mole fractions should be 0 if our guesses are correct. Well, we have our guesses in here, our initial guesses from up here, and we have our, oh, you know what? We don't have our initial guesses in here. Wanna know why? Because I messed up the equations. So I think I need to go back and put those initial guesses in. Because we have y1, n2 is, n2 is just, that's n2i, and that's n1i, and we don't even have those defined. I am going to look through this for a second, see if I can, you know what? Let's see if this results. I think that's what our problem is though. N2i and 1i. These are our initial values. Okay, cool. So now that we have that, let's see if this works. No. Where's MVP? We want to return this. Where's MVPs? Solve one. Okay, so what we're gonna do is we know that this is initial. I don't think these are supposed to be initial. Okay. Okay, so with that, we know that we have our values are not 0 for our mole fraction of both acetone and methanol. And knowing this, we know that we need to define more or wait, no, we're not. Sorry, I'm getting ahead of myself. Before we need to define anything else, we know that if they're not 0, then our guesses aren't correct. Now, they can be very close to correct, and we're really hoping that we are really close to correct, because then we can find the actual molar flux of acetone and of methanol. But this determines that we don't have it correct. Actually, my computer's going to die, so I'm going to grab a charger really quick. Give me a second. All right, I'm back. So now that we know that we didn't get a return of 0, we know that sorry, I'm gonna sit down for a second. We know that the more our guesses were wrong, and we need our molar flux values to be determined when this when the mole fractions of our acetone and methanol are 0, because they're going to be 0 at eta. So now we're going to go and determine those. Well, in order for us to determine those, we really need to define something outside of this whole the things we've already defined. Well, what we need to define is we need to define a function so that the molar fluxes of the molar fluxes, and what that will do is we can now say, okay, well, the molar flux of component 1 is going to be the first value in this array, just as we did above in the molar fluxes. And okay. And the molar flux of component 2, methanol, will be the second. And knowing this, we can now try to find our molar fluxes by putting this outside, or well, I should say, defining this all in the nested the nested loop of this. That's what I'm trying to say. So I'm going to create a nested loop where this it'll output this, but only when this is true. So only when we actually have our mole fraction of methanol and acetone equal to 0, we'll then get to the output in an array of these two values, which will give us the molar flux of acetone and methanol when eta is 1, which is beautiful. So now we're going to just clean it up a little bit. Sure, all this spacing's good. It's fine. So we're now going to go further with this. Let's just see which that works. And we're going to
use a root solver so that we can take all of this function and solve for our molar fluxes that we're talking about up here. Because we now are defining the molar function or molar flux, and then the molar, this whole cell of IVP within the Stefan-Maxwell diffusivity equations, but we're doing it all within there so that we have a true, when this is true function, we spit this out, but we need to solve for these roots. So we're going to take a root solver, and we're going to first see, what does a root solver need from us in order for us to be able to use it? Well, we see that we need a function that's callable, vector function to find a root of, and an array, an initial guess. Okay, so we need an initial guess, and we need this callable function. Well, good for us, we just defined a callable function, f, which we can put in this beautiful root solver. And our initial guesses, well, what are our initial guesses for the molar fluxes? We already have this, N1i and N2i. We just found those in part 1. So we're going to do N2i. And we're going to try to use this good old root solver, see what it says. Oh, it says we've got a problem.
All right, there we go. We finally fixed that error. So with that error fixed, we see that the root has solved, the root solver has solved for the molar flux of acetone and methanol at 8 equals 1. So with that, we are going to actually go and rearrange our code, because though we know this works, we want to put this in our functions instead of having it just lag back here. So what we're going to do, we're going to go up here, and we're going to define, let's call it root result. So root res equals root. And what we're going to do is we're going to take N1 here, okay? And we're also going to put that. Oh, wait, sorry. I'm going to delete these. I don't know what I'm doing. I'm not going to define N1 twice. We do N1 equals root res dot x and the first term of it, of this array. I meant to do bars 1. Oh wait, no, it'd be the 0th term. What am I doing? And then we also have the N2 would be exactly the same thing, but it'd be the second term, so it'd be the first. We start count at 0, so 1 is the second term. So we're going again, root res dot x first term. Okay, because what this will do now is it'll go to the root solver. Instead of defining it as N1 equals the first term in an array, it actually goes N1 equals the root solver first term in the array, and then the root solver second term in the array, which we just figured out works over here. So we know that if we have N1 equal to root res in the first term of the array, it's going to give us right here the value of the molar flux of acetone, and this N2 will give us the value of the molar flux of the methanol. So going on from there, we're actually going to start working on plotting our eta versus our molar fraction of the 3 compositions. So here we go. We're going to start off with we're gonna plot eta. So we're just gonna create a variable called plot eta. And what we're gonna do with this plot eta is we know the eta is going to range from 0 to 1. So first we're gonna define the range of this eta plot variable. And we're actually gonna do this thing. Oh wait, I don't know what I'm doing. That's not the first thing I want to do. Sorry. First off, I want to call in a function from numerical Python. It's a line space function. So we know that we're going to have, again, this range from 0 to 1, but we're going to do the line spacing in between from 0 to 1. And we're just going to pick a number. My professor did 51. It seemed to go well. So we're going to do 51 as the line spacing number. And that should give us a pretty good spacing so we can see our graph. Like that's a space between the lines. So for when it's ranging from 0 to 1, that produces a pretty good graph for us to see the molar fraction of all the components pretty well. So we're going with that. Oh, nope, I actually need to do one more thing before I move on. We're also going to take, so there's a plot of eta versus the mole fraction. So for each component. So what we know, we found the mole fraction for each component at each value of eta earlier in the res IVP solve, but or well res IVP originally, because then it was equals to solve IVP of that whole function. So we know that with this res IVP, we actually have every single value. Well, we have the molar fraction of each composition for every single value of eta. Well, using that, we can, so let's call in a function. I'm going to say this is a solution of the y's, because these are solutions from the earlier of our mole fractions for every value of eta. So I'm going to say solution of y equals res IVP dot solve. That's what we have from earlier. But instead of just solving it at one value of eta, which is 1 earlier, what we tried to do just at the top of the Stefan tube, what we actually want to do is we want to solve it at every value of eta because we're trying to compare it to eta. So what we're going to do is we're going to do plot eta, and it's going to give us every value of eta.
All right, well, now that we have made these two relationships for the axes, one for the eta and one for the molar fraction for each component, we are now going to just start plotting these on into a figure. So first of all, we're going to just make a variable called figure. And we're going to do a subplots. And when we make these subplots, the first thing we have to do is we have to decide how many rows, columns, all those things we want. So we just, I mean, this one's pretty easy. We just need one row, calls equals 1. We'll go ahead and we'll label our x axes and our y axis. That way we just don't get confused with which one's which. It's easier for the viewer to see which one it is. So x-axis, of course, is our eta, and we're going to capitalize that. And then our y-axis, of course, is, sorry, my typing and my talking at the same time has not been good throughout this video. Y-axis will be, of course, our. Now knowing this, we just have to make the we have to graph each function. So each component's gonna be different. We're gonna graph each one individually really quick. So we know that we have figure. I think it's add the figure. Let's just try that figure. Add. So figure add subplots. I know it goes scatter. Let's just impart no for now. Scatter. Go dot scatter. You know what? I'm just gonna try this all again. Okay. Figure dot add. Wait, it's underscore something. Trace, I think trace. And then this is where the geo scatter comes in. So graphed objects we've defined earlier. So trace geo dot scatter. Now there we go. Okay. So what we need to do is we need to set the x part of our like the x plots. So all the points of x equal to something, which of course we just already made that up there. So all we need to do is just plot eta. We already made plot eta equal to all of our values between 0 and 1 for eta. And then for y, it's a little bit more complicated, but again, we already made this up here. So we created this array of sol y with all these solutions, with all the arrays that we created from the res. Gosh, why can't I get that? Sorry, just give me a second. It's a long video. Okay. So with our solve IBP, all the results of our IBP solution, I put into an array, into all of these arrays, and it's a different array for each value of eta. Well, so if it's a different array for each value of eta, we know that for each array for the values of eta, the first term is going to be our acetone. So first term, we know that Python starts at 0. So we're going to go ahead and do that. And then we're just going to name this or name each graph. That way we can tell them apart. So acetone. And you know what? These are very similar. So I'm going to go ahead and I'm going to just copy and paste this to the next line because we're only going to have very small changes between each line. So of course, it's not going to be acetone again. It's going to be methanol. But also, we know that methanol is not the first term, it's the second term. So in each array, the first term is going to be acetone, second term is going to be methanol. So it's going to be 1 there. And then we're going to do this copy and paste again for our third component air. But this is where it gets a little bit tricky. So we don't actually have air in any of these arrays. Remember, this is just all we put in these arrays was we just put acetone and methanol. But knowing what we know about mole fractions, all we have to do is take 1 minus what we get the whatever we get in the array of for acetone. So wherever we get the mole fraction to be for acetone, and then whatever we get the mole fraction to be for methanol, because they all summed up together have to equal 1. And there you have it. Let's see what happens when we shift enter. There you go. Get this beautiful graph with mole fractions on the y-axis and eta on the x-axis. So it's going from eta 0 to 1. There's no units for eta or mole fraction, but we do see that as air or as eta increases, the mole fraction of air increases, and as eta increases, the mole fraction of both methanol and acetone decrease. And as they go to 0, the mole fraction of air goes to 1, which makes sense because the sum of all 3 of these always has to be 1. So there you go. I hope you enjoyed this problem and I hope it helped. Thank you very much and have a great day. Goodbye.